Hello and welcome to this lecture of Chapter 5, Foundations of College Chemistry. I'm going to be quickly going over early atomic theory and structure. If you need to pause the video to write down notes, feel free. Alright, let's go ahead and get started. Let me make this as big as possible. Alright, so here is what we're going to be going over. There are some YouTube video sources that I put on the FOCC Chapter 5 and Chapter 10. Please refer to those. Those are already loaded in Canvas for you. Alright, early theories on structure of matter. We talked about these early models. I'm not going to be testing you on this, on Aristotle or Democritus or Empedocles. If I pronounce that right, I pretty much am going to be starting with Dalton. But know that at some point there were philosophers that did speculate on what all matter is made of. Here's Dalton's 6 postulates. We do know that he is called the father of atomic theory. He was the first one to come up with general guidelines of what every atom looks like or follows in ratios. We do know that some of these are now incorrect. Make sure you understand that there is issues with postulates 1, 2, and 3. Now, Dalton, he didn't have this illustration, but this kind of shows how hydrogen and oxygen, given a chance to react, they can form water, or in C here you see H2O2, which is hydrogen peroxide. Okay? So, revisions to Dalton's theory is that elements can decompose under certain conditions. So these are the things that are wrong with his original postulates. Not all atoms of the same element are identical in mass, and atoms are not indivisible. Atoms are composed of subatomic particles. We know that they can be divided. So, 5.2 is all about Coulomb's law. Here's the properties of an electrical charge, which you need to know. I went over the different parts of Coulomb's law in the FOCC study guide key. Make sure you know what Q and R is, and if Q and R are changed, how that affects the force or the energy needed to break bonds. So the discovery of ions, this really came from, it started with Thomson with his cathode ray experiment, where he discovered the negative parts that were kind of stuck into the positive parts of the atom. He coined electron, but later on it was cations and anions that were coined as positives and negatives. So you've got Faraday, who discovered electrolytes, and he discovered that some compounds will decompose in water, and that they were either attracted to a positive or a negative side. So this little picture here is kind of like a really makeshift battery, basically. He had a positive rod and a negative rod, and he saw that certain things were attracted to those rods and kind of stuck to those rods. So he was the one from Thomson's work that kind of came, and Millikan's work with the oil drop experiment, that came up with the word ions. So here's the nature of ions. They typically have a positive and negative charge. The cathode or cation side is positive. The anoid or anion side is negative. So it's based on Faraday's and Arrhenius' work that the Stoney proposed that electrons was a fundamental use or unit of electricity, and it was Thomson that later found the existence of these electrons. So they were kind of all working together on this. Here's what cations and ions look like, where sodium loses an electron and goes down in size. Some metals can lose more electrons and become a higher charged cation, or nonmetals accept electrons and become more negative and larger in size. Subatomic particles, what I want you to know is their electrons, protons are positive. I'm not really worried about size here, but know where each part is. So the nucleus composes of neutrons and protons, and electrons are on the outside of the nucleus. Okay, so here's the discovery. I'm not going to get too much in discovery of neutrons, protons, and electrons. You do need to know they are attributed to certain people. Chadwick was the one that was attributed to the discovery of neutrons. Protons, pretty much that would be Rutherford, and electrons were Thomson. All right, here's kind of the summary table that is on your FOCC key. Chemical properties of an atom is based on their electrons, protons, and neutrons and how many they have. Here's the structure of an atom and where they're located. Here is the cathode ray tube that Thomson used. Here's Thomson's model of the atom. Sorry that picture is kind of in the way. These purple circles are like the negative parts in the beige positive parts of the atom, and it's called the plum pudding or chocolate chip model. Plum pudding is English. It's pudding with raisins, basically. So the things that are inserted in the positive stuff or the main part of the atom. So the cookie part or the pudding part would be positive, and the raisins or the chocolate chips would be the negative electrons. Apologize for these pictures being so small. Let me try to blow these up a little bit. This is Rutherford's experiment, the gold foil experiment, where he shot alpha particles at a gold piece sheet. There were some that deflected straight back, some went that straight, most of them went straight through, and then some were deflected sort of at different angles. So he surmised that the ones that were deflected straight back were hitting, this center dense part of the atom. So he pretty much coined nucleus. He was the one that came up with nucleus. And he also discovered that since most of the particles went straight through, that the atom must be made of mostly empty space. So it wasn't this everything was positive with these little negatives stuck in like Thomson thought, but he looked at the atom as mostly empty space, and that the centralized dense nucleus reflected particles back. So everything must be centralized in the center of the atom. This is just more on the nucleus, its size, and how it's mostly empty space. And then here's the history of the atom. Now, I'm not requiring you to know every one of these people, okay? The big ones are Dalton, the father of the atomic theory. Then you've got Thomson here, who came up with electrical discharge, discovered the electron. Rutherford with the gold foil. Positive charges were centralized in the nucleus. He was the one that coined that. And then Bohr. Now, all of these other gentlemen have important, additions to the history of the atom, but those are the big four that I'm asking you to know. Here's like a makeshift and easier one. There is a TED Talk. If you just type in history of the atom TED Talk, you'll come up with this YouTube video. These are the models I want you to know and who they're attributed to. And actually, I'm going to, I want to zoom this in just a little bit so you can kind of see the reading. And then here is, there's that more central, so if you need to pause the video so you can read the reading and put that in your notes. Here's another one. It's kind of really cut down and simplified. Let me zoom this out just a little bit. The atomic number. So the atomic number tells you how many protons, neutrons, or how many protons and electrons are in the atom. It also is the identity of the atom, because protons cannot change. If you change the number of protons, then you change the element. Okay? Isotopes of elements. Isotopes are when the number of neutrons change. So protons can never change. If you change protons, you're changing the element. If you change the number of electrons, you're making the element more positive or more negative. You're changing its charge. Okay? If you change the number of neutrons, then you're changing the isotope of that element. Okay? So here's an example of how hydrogen has two different isotopes. We have 1 proton, 1 neutron, 1 proton, 0 neutrons, and then you have 1 proton, 2 neutrons. Okay? So the most common one is protium. Okay? So here's the generic way of writing isotopic notation for an element. E is the symbol, A is the mass number, and Z is the atomic number. Mass number is the number of protons and neutrons added together. To find the number of neutrons, you take mass number minus the atomic number, and you get the number of neutrons. Here's like an example of hydrogen, oxygen, sulfur, and fluorine, and ion. How to find, if you're given the mass number, the atomic number, how to find neutrons. And then identifying subatomic particles from isotopic notation. Here's the example of copper, where you have a mass number of 64. The atomic number is 29, so there's 29 protons and 29 electrons because it's chemically neutral. All elements are chemically neutral. That is the assumption. And then to find neutrons, we take the mass number minus the atomic number, and we get 35 neutrons. So pause the video. Some of these were on your FOCC study guide sheet. But go ahead, pause the video, read the question, and try to answer. And here's the answer. Atomic mass. Atomic mass is pretty much based on carbon-12. Now, I don't get into this too much with my students. This is more a Chem 151, 152. But basically, atomic mass unit is equal to 1/12 of the mass of carbon-12. How do we calculate isotopic distribution and AMU? Well, it depends on the percent abundance of each individual isotope. So here's like an example. We have copper 63 and copper 65. We have the isotopic mass. The isotopic mass doesn't match the mass number, so you can't just assume that. Then we have the percent abundance. We take that. Now remember, this is percent, so you got to put it in decimal. You're not taking this number times 69%. You wouldn't get 43. You would get, really high, like 300, 400, number. So you have to take this and multiply it by 0.6909 and get this number. And then you add those two masses up, and you get an overall average mass unit for the periodic table. Measuring abundances, well, here's another way of writing it. I know this is kind of messed up a little bit. Let me try to move this around a little bit. It's like on there double, sorry. There we go. So you're taking the atomic mass times its abundance plus the next atomic mass times its abundance to get the whole. Or you can see it from a graph. Here's the mass number, here's the percentage peak. So we have a mass number of 63 at this percentage, a mass number of 65 at this percentage. You could do it either way. Right? So here's another example. And then let's practice. So stop the video, write out the isotope mass and its abundance, and then do the calculation, and then see what AMU you come up with. All right, here's your answer. You should have gotten D, and there's the breakdown of the math. All right, so here are your learning objectives. These are what's going to be tested on this upcoming class. So please make sure you review this PowerPoint, and I will see you in class.